Okay, so in the first half of chapter 4, we talked about scatter plots and what those look like. Today we're going to talk about this very last term here, which is correlation. Correlation is a measure of both strength and direction. So we talked about how with a scatter plot we could say that it's strong or weak in its relationship. And then we talked about its direction as being a positive or a negative relationship if we're looking at a linear relationship. Correlation, the book defines a big formula for correlation on page 100. It is ridiculously overwhelming to look at that formula.
Or compactly.
Yeah, or compactly, because then it does the Greek sigma thing, which means add them all up. Basically, what it's doing is, underneath it even says, like, it's a bit complex. But you should probably use software to do it, which is how we're going to be doing it. What it is doing is it says it begins by standardizing the observation. So it's basically finding kind of like the idea of a z-score for each of the data points. And then giving some measurement of that. It's not just a z-score, but that's kind of what it starts with, is the idea of a z-score. And then kind of taking like a z-score of the x's, a z-score of the y's, multiplying those together, and adding them up is what the formula says, and then dividing by n minus 1, so kind of like finding an average of them. So it's kind of like finding an average of the product of the z-scores, in a way, loosely is what it's doing. We're not ever going to find these by hand, ever. So we will use technology to find our correlation, which is given by the letter R. But the important things to know about it, it measures both strength and direction. And then on page 101, there are 4 bullet points here that are really important to know about correlation. And the first thing is that it makes no distinction between variables. So if you switched your explanatory and response variable, so like some of you made your scatter plots backwards on the homework assignments, your correlation would have been exactly the same as anybody else's. Okay, so correlation doesn't distinguish between which variable is explanatory and which variable is response. The second one there says that because we're using z-scores or standardizing values, that units don't matter. And R itself has no units. Our correlation coefficient has no units. It's just a number that talks about how closely related these things are. It itself has no units. The third fact about correlation that's on there is that a positive R indicates a positive association, and a negative R indicates a negative association. So that's how it tells us about direction. And then the last one here is how it tells us about strength. That correlation is always going to be between negative 1 and 1. 0 is weak. And then close to either negative 1 or positive 1 would be strong in either a negative direction or a positive direction.
Will this make more sense when we do an equation?
I hope so, if it's not making sense now.
I mean, it's just rules.
So, yeah. So then on page 102, it gives us 6 different scatter plots that we can kind of look at to think about what correlation would be like for those. So the first scatter plot is totally random. If you were trying to draw a general line to show that pattern, you would have no clue where to draw that line. And so that is an R value of 0. Okay? An R value of 0 is a very weak relationship. Essentially, an R value of 0 is saying there's no relationship between them. Then the next one over says that it has an R value of negative 0.3. Okay, so negative tells us that in general there's kind of a downward trend in the points, but 0.3 is pretty close to 0, so that's a pretty weak relationship that we're seeing there. The next row down has an R value of 0.5, positive 0.5, so we see a general positive relationship, and it's a little bit stronger than the other one because 0.5 is closer to 1. Negative 0.7 for the next one. Negative tells us downward trend. 0.7, the closer we get to 1, the stronger the relationship. So we're seeing these points kind of tighten up together. The next one we've got positive 0.9, positive, so it's going upward. 0.9, so that's a pretty strong relationship. And then negative 0.99, those are like in a straight line, and it's a negative straight line. Okay, so that's what our last two of these rules say, is that a positive R, we should expect a general upward trend, and negative R, expect a general downward trend. If it's close to 0, it's just a completely random looking scatter plot. If it gets close to 1 or close to negative 1, we're going to see a distinct line forming. Okay, and then the first two just tell us if you graph it backwards, you're going to get the same answer for correlation, and that units don't matter. So when we report an R value, we should never report any units on it. And if you change your units in your problem, so like if you originally were doing some sort of a data collection and one of your variables was the length of something, it wouldn't matter whether you were measuring that length in inches or centimeters or feet or what. You would get the same R value no matter what units you used. Okay. On page 103, there's 4 warnings about correlation. Okay. The first warning about correlation is that it requires both variables to be quantitative. We can't do this if we're talking about categorical things. Okay, because the formula is using arithmetic. It's basically finding an average of a product of z-scores. Those are all number things to do. So we can't do this if we're talking about blue and red and brown and green. Okay. The second caution is to make sure that correlation doesn't describe curve relationships. Correlation is strictly a linear relationship measurement. So in one of our homework problems last night, we saw a curved relationship. We shouldn't talk about the correlation there. It was a very strong curved relationship, but we wouldn't talk about a correlation value there.
Wait, so if there is a curve, we don't talk about
correlation? Yep, correlation is for linear relationships only.
But if it's straight, then you talk about
Yep.
Okay.
The third caution is, like the mean and standard deviation, the correlation is not resistant. That means that it's strongly affected by a few outlying observations. So outliers have a big effect on correlation. Outliers, bad. Okay. So just like our mean and standard deviation, if you have one piece of data that really doesn't fit the trend, it really changes your mean or standard deviation. Same thing with correlation. And the last one is that it is not a complete summary. Okay, so a lot of students just want to give a correlation coefficient and say that that tells everything we need to know about the relationship, but we really also need to give the mean and standard deviation along with it. Okay. We use the mean and standard deviation when we're talking about correlation because that's a part of the correlation formula. So we don't talk about correlation in 5-number summary, okay? Because the mean and standard deviation play into how correlation is calculated. We want to give mean and standard deviation along with it. So we give X bar and S also. So to avoid using that huge messy formula, what we want to do
To find the exact correlation.
to find the correlation, yep. So we can kind of guesstimate when we look at a graph. I mean, we could at least say, is it going to be closer to 0 or closer to 1 or negative 1? You know, strong, weak, positive, negative. We can just kind of guesstimate those general ideas, but to actually find the correlation, since we're not going to use that disgusting formula, you would go into your stats and into your list where we put in our data. You would, again, just like to make the scatter plot, like we talked about in the last lesson, to have the calculator make the scatter plot for us, you would need to put your data into your L1 and L2, and you need to make sure that when you've entered all your data, that those two little dotted lines are right next to each other so that all of our data is a matched pair. Okay. Then to find our correlation, so I'm going to quit out of there. To find our correlation coefficient, what we need to do is, and on some of your calculators, I actually want you to like all do this on your calculator, not just watch, because some calculators have it turned off, that it won't tell you your correlation coefficient. So if that's the case, I need to turn it on for you. So what we need to do is go into Stat, over to Calculate, and we're going to choose choice, it's 4 on mine, but it should be around that on yours, maybe 3 or 4, that says LinReg.
Oh, yeah.
Okay, we're going to choose choice 4 on mine, but whatever one says LinReg, and hit enter, and enter. Will actually give us some information here. It's thinking hard. Okay, and mine it's not on, so it doesn't give me my R value here. So yours might tell you an R value at this point, and if it does, you're good to go. If it doesn't, this is what you need to do. Press second, and then the 0 is my catalog button. And then I need to scroll down, they are alphabetical, to the word diagnostic. Diagnostic on is what we want.
Okay.
And I'm going to hit enter, and just hit enter again, and it'll say it's done. Now if I go back and do my stat, calculate, linear regression, now it gives me my R value.
Okay.
It also gives me something called R squared. We're not going to worry about that at this point. Just R is our correlation coefficient. And so for this data that I had in my calculator, about 0.56. So it's a medium strength positive relationship between these two variables in there. Yep, I'll go through and find it with you on you. It's diagnostic on is what you want to look for.
So then you have to turn on every time?
No, once it's on, it will stay on. So that's just something we just need to turn it on, and now it's on, and it'll be on forever, and we'll be set to go there. But we just need to get it turned on.